So yeah, a little bit of a background on Ericsson here. So pretty young company, started in 2020. Focusing mainly on concrete condition assessment in the hydro space and bridge space. Started with three projects. Um, in 2020, in British Columbia, Canada. 2021, we moved to the U.S. Started to do our first projects down there. Um, Worked with some of the major dam owners, um, and asset owners in the U.S. And then this year, we're on track for about 60 projects, and expanded to Australia for the first time, which is pretty exciting. We're also part of the Bentley Eidswind Ventures network, so we're a network company, and we're really excited. We like the work that context capture does, and we'll kind of get into a little bit about that later. But I want to talk a little bit about this from the um, civil engineering perspective here. Infrastructure is not getting any younger, right? So inspection work, particularly on civil assets like dams and bridges, are getting ever more important. Um, and we all kind of are familiar with some of the traditional assessment methods for infrastructure. Sometimes it can be depending on the level of complexity of the structure, as well as the amount of detail that's required for a particular inspection. It might be, we might need some rope access. We might need a snooper truck or a boom lift. We might need to do some sounding of the concrete and maybe even some crack mapping. And so all this work can be, again, depending on the level of detail and the size of the structure, can be a little bit laborious, time consuming for engineers. Our idea was, could we come up with an inspection method to not only improve the speed of the inspection, but also, I think more importantly, make the inspection repeatable. What we want to do is go out there, capture high resolution imagery, and then build a baseline so we can start to track, how this asset is changing over time. So what we're going to do is pair some robotics data collection techniques, using some UAVs, and as well as image processing. So can we use some image processing techniques to automatically map and quantify some of the cracks, falls, and other defects that we see on some of these structures? So just kind of give a high level overview on the workflow that we use. So typically when we work with an asset owner, we'll go out, work with some third party drone providers or with the client's drone providers, and we'll capture some extremely high resolution data. So on the top left there, you're going to see, M300 capturing imagery at 1 millimeter per pixel resolution. So pretty high resolution imagery. We're about 8 meters away or 8 yards away from the structure. And on the bottom left and the right side of the screen, you're going to see the Skydio being deployed on a bridge structure. And then on the right is also a Skydio for a hydro structure. We use completely automated flights with our partners. So we want to capture consistent high resolution imagery from these structures. And the purpose, again, coming back to that repeatability element, we want to be able to track, build that baseline, repeat the flights from year to year, and start to track how these structures are changing over time, right? And then the next step is, our proprietary acoustic sensor. So I'm not sure how many of you are civil engineers, but typically, a civil engineer will be able to inspect the structure. We'll do some soundings with a hammer. So we'll go out there, touch it, hit the structure with the hammer and listen for any hollow feedback, right? So we invented an acoustic device that replicates that same methodology. The drone actually touches the concrete, sounds the structure, and then records the vibration and sound response. So you can see that in the videos here of the device hitting the structure. And then, so what do we do with all that data? So using obviously context capture, we produce a 3D model. Each one of these green dots represents a location of where an image was captured. So on the right side of the screen, you'll see the dam, and on the left, the bridge. But so one thing I always say is, it's great to have a 3D model, but at the end of the day, we really need to derive some sort of insights, from these 3D models, right? And so I think that's really where our technology comes into play. So, on the left there, you're going to see a 3D model we generated of a bridge asset, using Bentley's context capture. And then on the bottom right, you're also going to see a hydro dam. And one thing I just want us to pay attention to is the level of detail and resolution from that automated flight and that, 1 millimeter per pixel resolution imagery. Um, so I'll let it play for a second here. But then one thing that often goes into, um, that I say is, this particular dam, for example, on the right side of our screen has thousands of cracks, thousands of spalls, leakage coming through various cracks. That's kind of pointed out by the white mineral deposits on the screen. And so, one thing that can be really challenging is, okay, how are we going to actually map all of these defects, cracks, spalls, and actually start to get some insights into, okay, how deteriorated, is our structure, right? So I'll let it pan around here for another couple seconds. The resolution here is so high that we can actually start to see the individual threads on the rebar that's exposed. So that's kind of the level of detail that we're able to achieve. But then the next step is, okay, how are we going to actually, make sense of this data? So this is some of the example of the, results of the acoustic sounding that we do. So just to kind of give a high level overview, delaminated concrete, we're taking the sound profile as well as the vibration profile when we strike the concrete. So we literally have a piece of metal that's attached to the drone. It strikes the concrete, and then we have a microphone and an accelerometer that records the sound as well as the vibration response. And so this is an example of the vibration response here. What you can see, this is 3 strikes at the same location. And so drones out there hitting the concrete, and we're recording that profile across these 3 strikes. So you'll notice some minor differences between the three samples, but generally a pretty similar trend across all 3 strikes. And similarly for sound concrete, we have 3 strikes at the same location, with a similar trend across all 3 strikes. So we're pretty excited about being able to actually track, from an objective standpoint. So instead of having the human go out there and hit the concrete, listen with the ears, let's have the device, start to objectively track how this information is performing over time. And what's kind of the output as a whole? So on the top left, you're going to see a bridge project we completed. On the bottom right, you're going to see a hydro project. We have this tool. It's a cloud-based tool called AutoSpecs. We cut up everything into 2D. So based on the engineering drawings, so all these are just 2D files that we can actually overlay into the CAD environment or into any GIS environment. So pretty useful for engineers to make maintenance decisions, as well as do some further structural analysis on these structures. As you can see, we've got all of the information color coded here on the right side. Cracks are color coded based on their width. 0 to 5 millimeters is colored green. 5 to 10 is color coded yellow. Anything above 10 millimeters is color coded red. And then we've also got our spalling layer. So all of our spalls have IDs. We can quantify each one of those spalls. And similarly for our bridge structure, right? So we can zoom in, navigate around our bridge structure, turn on our various layers. We've got our delamination layer here in the top left corner. So red indicating delaminated concrete, yellow indicating unconfirmed, and somewhere in between that sound and delaminated concrete, and then green indicating that sound concrete. And so we can start to overlay all these layers on top of each other and then quantify. So if you look in the top left here, we turn on our crack ID layer, we turn on our spalling ID layer, we click on it, and we see the surface area of our spall, 8,586 centimeters squared. We can zoom in, see each individual crack, turn on our ID layers for our cracks, and see what the particular length and width of a crack is. So we see about 2.4 millimeters wide and about 60 centimeters long, and same for our hydro structure here. What's interesting, we've also got a density grid. So, one of the structures we worked on suffered from AAR. And so one of the key challenges for them was they wanted to understand, where the defect was located. We can overlay our thermal layer here and start to see seepage. And so, the great point about this platform being able to use the density grid, we can see at the click of a switch where the highest density of deterioration is located on our structure. So, where is most of my spalling occurring on the structure, and how significant is it? So we can see where the highest density of spalling, for example, on this hydro dam is in this particular area. We can see the highest density of cracking, for example. So we might be able to use this to identify, where some future spalling may occur at our structure, based on how severe the cracking is at a particular location, and start to see trends. Like, for example, most of the cracking seems to be occurring in the middle section of this retaining wall here for this dam. But moving on, taking this kind of back to a high level, again, we want to start to track how these structures are changing over time, and also start to help, use this information for asset management purposes, right? So this is really, at the end of the day, a baseline, right? So we'd like to take that baseline and use it for monitoring to start to track how these structures are performing, over time. So on the bottom left there, you're going to see a survey that we completed in 2021. And on the top left, you're going to see a survey that we completed in 2022. And what you'll notice is a small propagation, or the small formation, rather, of a crack on one of these structures. And so what we've developed is a tool to automatically, detect that change. So what we do is we take those layers. We have certain error bars, right, that we set to help, offset the error between two different surveys. And what it does is it actually subtracts the two surveys. So survey 2, we can take the cracking in a particular box, and then we can subtract that from the box in the previous survey. And so, same concept. At the flick of a switch, we can start to see, where the asset had changes, in the structure between different surveys, which is pretty exciting, we think. And of course, what's kind of the purpose of this data, right? So how can this be used from a civil engineering perspective? So, the most obvious one is monitoring, right? Starting to track how changes are occurring on our structures from year to year. And, this is really important because, not only do we want to start to track how these structures are changing over year to year, but we can actually start to use this information to build predictive models, or predictive deterioration models. That's really where we're headed as a company. So, right now we're starting to collect baseline data and change detection data between assets from year to year. But what we want to go is actually towards building these predictive models for these assets and predict, where we need to prioritize our capital investment from the administration level. So that's one way that this type of data can be used. Number 2 is for rehabs and repair, right? So, using some of this information, we can start to calculate section loss. So particularly from the bridge inspection or bridge, perspective, really important for load rating for bridges, especially as, trucks get heavier and cars get heavier each year, and they seem to be towing heavier equipment across these bridges. It's really important that, accurate section, accurate load rating is completed. So that's one way to use it. Overlay some of this information into CAD or GIS environment to do further structural analysis, or even make estimates for repairs, right? So since we've got the surface area of various spalls, and we can start to estimate the amount of material that's required for the repair, and start to do issue quantity contracts for construction contractors. The fourth one, identify potential failure modes, right? So depending on the type of structure, using some of this data might help us identify some potential failure modes of the structure. So Talking about spillways, for example, maybe we find some spalling along the joints or spalling at a particular location of a structure that's particularly hazardous. Or similarly, maybe we'll find some cracking in a particular area that's particularly hazardous for the structure. So maybe through cracking, crack that goes through the entire pier of a spillway, for example, or a dam. Um, the other type of work is we can actually just use this as a general digital twin. So if we've got instrumentation data on the site, we can start to integrate this digital twin into other types of data that we're collecting on the sites. And of course, we don't do everything, as a company for condition assessment work. So maybe, we need to actually do, identify crack depth, for example. So maybe we need to do some coring work on the structure to help identify what the depth of some of these cracks are for our structural analysis. Or maybe we need to use GPR to help get a better understanding of the quality of the concrete. And then, of course, there's some site-specific and asset-specific um, information or applications, such as using computational, the condition assessment data for computational fluid dynamics for a spillway structure, or doing finite element analysis, on parts of the structure that might be of interest. So just wrapping up here, and I'll turn it over to everybody else for some questions and comments. What's kind of the key takeaways here? So, obviously, I think, one of the most important for some of these organizations is improve safety for personnel. Um, with this type of technique for collecting data from bridges and dams, we're reducing the need for rope access and U-bit trucks, super trucks, boom lifts. So all this is going to result in improved safety for personnel by reducing the amount of time they need to spend on site. The other one that we've heard is actually improved documentation. Especially during COVID, a lot of organizations have lost structural engineers. They've had them retire, and they've lost all that institutional knowledge that used to, about that these structural engineers and civil engineers had. And so just having this, timeline of your structure so that we can start to go back and say, okay, when did that crack form? Was that, did that crack form during construction, or was that formed, in 2015 when some sort of earthquake happened, or some sort of significant event, or maybe it was just deterioration over time. So just having that, improved documentation to really start to maintain that institutional knowledge, and also scale inspections, right? So we can actually start to scale the number of inspections we're doing because of how quick, this type of event is. And then, the last component here is just kind of shifting the mindset of the industry. So, I'd say most of the, civil industry is very much on a kind of a reactive basis for repairs. But with this type of technique, and getting the baseline and starting to track how it's changing over time, we can really start to shift towards a more of a preventive maintenance and predictive maintenance point of view, and start to really get at an objective and quantifiable methodology for prioritizing our repairs from an asset management and maintenance perspective. So that's kind of a high level overview on some of the work that we're doing, with at Nearson, and thanks to the help of Bentley for their great work on building 3D models. But maybe with that, I'll turn it over to you, Greg, and we can close it.
Yeah, thank you, Josh. Appreciate that. Incredibly informative. That is really good stuff you guys are doing there. Let me see. Okay. Get back over, and we've got a couple questions here coming in, Josh. Let's see. Okay, yeah. What are some of your challenges with regards to implementing this technology at various civil asset locations?
Various challenges with civil assets.
Yeah.
Yep. Yeah. So that's a great question. So really become site specific. Some of the ones that each site can have its own individual challenges, and one example that might be present at hydro dams, for example, is actually electromagnetic interference from the site. from the generation of electricity. So, being aware of that and using some different equipment can be really useful. The other thing that can be challenging is lighting concerns, particularly around bridges. And so, using some techniques and equipment to make that improve the 3D model and improve the output of the results. Those are some various challenges at a high level.
Mm.
Um, if that answers the question.
Yeah, cool. And let's see, we have another question here. What size of the sites can this technology be deployed on? What's the largest site you've worked on?
Yeah, largest site. We've worked on the third tallest arch dam in North America. So that was about what is 150-meter tall. So
Wow.
about 600 feet, 500, 600 feet tall dam in Northern California. So it took us about 10 to 20,000 photos that we had to process
Mm.
using context capture, and it turned out at 1 millimeter resolution. So it turned out really well. Um, but yeah, no, that's the biggest project we've worked on.
Fantastic. Okay. Let's see. I don't see more questions. So we'll go ahead and close and wrap up. Just wanted to share a few more slides with you guys with some upcoming stuff. Please reach out to myself, Josh, at Nurickson. Be happy to contact you guys if you guys have some interest in learning more about Nurickson and what they're doing. Of course, reality spatial modeling. Please contact me on LinkedIn. Happy to talk with you and see what we can do for your business. Would highly encourage everybody to check out Nurickson's website. The story behind it is quite incredible. Harsh, the CEO, has done a great job with Nurickson and providing, these preventative things for assets, to keep people safe. So check out their website.